Right, welcome everyone to this week's Iowa Learning Farms Conservation webinar. And we are really fortunate to have Dr. Emily Waring with us. I am Matt Helmers. I'm fortunate to get to co-host many of these, and specifically this one gives me great pleasure to host. I am a faculty member in the Department of Ag and Biosystems Engineering and director of the Iowa Nutrient Research Center, and also fortunate to work with the Iowa Learning Farms program. So Dr. Waring is a graduate of our Agricultural and Biosystems Engineering department. She worked with my research group for both her master's and her PhD, working master's with the Sustainable Corn Project and PhD with finishing some of, continuing on with some of that work, and also with then our Nutrinet project. And she's going to talk about one of her studies that looked at the impact of fertilizer timing on nitrate loss and crop yield. As always, if you have questions for Dr. Waring, please type those into the chat box and we'll get those to her at the end of her talk. With that, Emily, the virtual floor is all yours.
Okay, thank you so much. There we go. So like Matt said, I'm Emily, and I'm really excited to be talking about some Iowa stuff. Currently, I'm working in California for the USDA Ag Research Service in Parlier, which is in the Central Valley near Fresno. And it's very hot today. It's 112, I think. So happy to be working inside and talking to you guys. So I imagine if you're watching this webinar, you know about the Iowa Nutrient Reduction Strategy, but I just wanted to go over really quick why we care about nutrients. So excess nutrients affects communities locally and nationally. So here I have a photo of the, thank you. Here I have a photo of the continental United States, and then that highlighted zone is the dead zone, which cannot support marine life due largely to excess nutrients. And then on the bottom there, this is delivered incremental nitrogen yield, so kilograms per square kilometer. So darker is more nitrogen. So if you look at even like comparing Nebraska to Iowa, the cropping system is generally the same, but one large difference is that they have tile drainage. In Iowa, Illinois, Indiana, all of those are quite dark green. So the combination of annual cropping system and tile drainage leads to a lot of mobile nitrogen, and then that can be taken down to the Mississippi River, to the Gulf of Mexico. And on the right there, I just have a visualization of why we need tile. So there's a field without tile on the left, and then a field with tile. So in order to promote crop production in these systems that would otherwise be oxygen stressed, you have to introduce oxygen by lowering the water table, and then the crops can thrive.
To interrupt you too much, if you can just speak just a little bit louder. There was one person, I think, just
oh, sure.
Yeah, use your extension voice.
Okay, sorry. Thank you for saying something. Okay, now let me know if I'm too loud. But so the official Iowa Nutrient Reduction Strategy goal for non-point source pollution is 41% reduction, and non-point source pollution is largely agriculture in Iowa. So I'm going to come back to that, but that's the official goal. And some tools that we have for reducing nitrogen loss from tile drained corn, soybean systems. There's kind of two categories here. So edge of field practices such as wetlands, bioreactors, saturated buffers, and then in-field practices, as the name suggests, things that we're changing about the entire landscape. So like adding cover crops, changing tillage, adding crop rotations, and then changing the timing of nitrogen fertilizer. So the goal conceptually is very easy. We just want to get all of the nitrogen to the plant, and not anywhere else. But those nitrogen transformations are dependent on a lot of different factors. Some of them are controlled and some of them are uncontrolled. So in practice, it's actually quite difficult. So yeah, we're going to see how fertilizer timing influences that particular goal. And we had 4 different treatments of fertilizer timing in the corn year of the corn soybean rotation. And this was done at Northwest Research Farm in Cherokee County. And I just wanted to give a huge shout out to Landon and Andrew, who were the research farm staff, and Terry. They did all of the field work pretty much, especially the water collection. So they were out there collecting water samples twice a week for the last 6 years. And Landon is standing in a sump. So that will collect water and then we'll measure that for water quantity and quality. And that's done, like I said, on 32 replicated plots. So there's a satellite image of the 32 plots there. And then there's 8 replications each. So if we have 32 plots and 4 treatments, that means we have 8 reps each. And then there's corn and soybean present in each year. Because like I said, we're only applying fertilizer to the corn year. And those years are going to change. The response is going to change depending on the year because of weather changes. So I'm going to talk about the first 2 treatments here. So I'm going to call them fall and spring. And fall is applied in the fall in hydrous ammonia with a nitrification inhibitor at 135 pounds per acre. And 135 pounds per acre was the maximum return to nitrogen in, I think, 2014 or 2015, whenever they checked it for this particular site. So that's kind of like your bang for your buck nitrogen. And I do think that is low, probably compared to what most farmers would be applying, but that is the maximum return to nitrogen. And then the spring treatment is applied at pre-plant, and that's in hydrous ammonia at 135 pounds per acre. So I'm going to try and visualize what a nitrification inhibitor is. So on the left there, I have the diagram that I showed you before, field without tile and then field with tile. So you have all of this inorganic nitrogen floating around. So the yellow is ammonium, and then blue is nitrate. And the process by which ammonium changes to nitrate is nitrification. So when you add an inhibitor with your fall fertilizer, you're slowing that down. So you're keeping the nitrification, you're keeping the nitrogen in the ammonium state. And then here I have 2 happy plants because both of those forms of nitrogen are available for the plant, but only one is mobile. So I put a little running man there for nitrate. So then when you add a pipe there, then that nitrate is going to go with wherever the water goes. So that is the difference between the first 2 treatments, is that the timing, obviously one is applied in the fall and then one is applied at pre-plant in the spring. And then one has a nitrification inhibitor. So if we could keep that nitrogen in the ammonium state through the fall and early spring, that's the goal. We're going to see whether or not we did that. And then the third treatment is the split application. So urea is applied at 40 pounds per acre at pre-plant, and then 95 pounds per acre in season at, I think, B12. And then the 4th treatment is no fertilizer. So there's no fertilizer applied with corn or soybeans. And then one thing I want to highlight here is all of the 3 fertilizer treatments have 135 pounds per acre of total nitrogen. So for the split application, you could theoretically change the 95 pounds. You could add 45 pounds and then add the later in-season stuff based on like crop status, but I think it was Matt and John who designed this experiment, and they wanted to have a true test of timing rather than changing the amount. So everything just had 135 pounds of nitrogen per acre. And I'm going to go back. I just wanted to add that in hydrous ammonia, so it had the inhibitor in the fall, but then it was also applied to cold soil. So it was applied at 50 degrees and cooling, which is the official recommendation for fall applied fertilizer. So here is like a 30,000 feet overview water quality. So we have nitrate concentration, milligrams per liter. This is average from 2015 to 2020. And I wanted to highlight that corn and soybean had generally the same trends here. So fall and spring were the highest, the blue and the red. And then split application was lower than that, and then no fertilizer. And that continued into the soybean year, which is interesting. Then I added some statistics when I combined the two. So there's an N of 8 for all of these. And when we looked at it that way, when we looked at the whole rotation rather than just corn or soybeans, fall and spring had the exact same nitrate concentration of 11.7. And then since split application has a different letter, then that means that it's significantly different, which was lower. And then no fertilizer was lower than any of the fertilizer treatments. So that was like a large overview, but then I'm going to talk about a particular scenario with water quality, I guess, which in my opinion gives us a bit more confidence in what we fall and spring kind of having the same influence. So this is a fertilizer timing study, and the form of nitrogen is influenced by temperature, which in Iowa, obviously there's very large swings. So I'm going to talk about the timing seasonally of drainage. So on the y-axis, I have drainage in inches. And then this is just the 4 seasons from 2015 to 2020. And the first thing that I want to highlight is that most drainage comes in the spring, so from April to June. And that's because of precipitation. There's more precipitation then, but then also there's little to no crop water use, because if you plant in May or April, then the crops are very small. So the combination of those two things, a lot of precipitation and little to no crop use, means that most of the drainage and loss comes in the spring. Thank you. Yeah, so if you look at each individual year, most of the time spring had the most drainage. And then here I'm calling this kind of the worst case scenario. So at the beginning of the study in 2015, there was 4 inches of drainage, which is the second most of any season in October, from October to December of 2015. And then there was another very wet fall. So I just kind of wanted to, well, in terms of drainage water quality, that's kind of a very interesting combination, and we're kind of lucky that we get to see that extreme scenario and how fertilizer timing influences drainage in that extreme scenario where you have no crop growing. So this is from October to June. You have 9 inches of drainage, and we'll see what happened. But first I want to set the scene. So like I've been saying, that 2015 was the start of this study. Tile drainage was installed at this site in August of 2013, and then oats were actually planted. And then in 2014, all of the plots were planted to soybeans. So there's no fertilizer, no external inputs. And then in 2015, the treatment started. So now I have month on the x-axis from June of 2015 to June of 2017, and then precipitation and drainage. So these plots in June of 2015 had only been in soybeans. So soybeans growing June, July, August, September, October, and then these plants or these plots will go to corn. So then fall fertilizer was applied in mid-October. Then we got a bunch of rain and then a bunch of drainage because there's nothing growing on the landscape. So this is the same graph, but now I've applied, or now I put nitrate concentration over it. So here we have 4 lines, and those are the 4 treatments. So the first thing that I want to highlight is that all of the treatments were equal within soybeans in the first year. So there's no letters on here. So the blue is equal to, even though there's peaks and valleys, there's no statistical difference between blue, gold, orange, and purple. And that's just kind of nice because it proves that like our randomization worked, I guess, because all of the plots were theoretically equal, and it turns out that they are, before we applied any of the fertilizer treatments, because that was not applied until mid-October. And then the other thing that I want to highlight is that the soybeans were above 10 milligrams per liter. So this is without any fertilizer input. So yeah, the annual cropping system, even without fertilizer, still resulted in high nitrate concentration. And there is a caveat here, I guess, from June to October. The drainage amounts are really low, so like less than an inch, and some of them you can barely even see. So when you have very low amounts of drainage, like very low volume, that can result in peaks of nitrogen concentration just because there's so little water. But then it continues over here in all 4 treatments to be above 10 milligrams per liter. So now I'm just showing you more of this graph through time. So again, for fall fertilizer was applied in mid-October, big drainage events in November and December. And then, can you see my mouse? Can you let me know?
Yeah. Yep, I can
okay,
at least.
Nice. So then big precipitation events again, especially in April. I think that's interesting because we would expect delayed nitrification. Then you get to April, and if you look here, the fall and the spring still have the same nitrate concentration. So that means that the inhibitor is working. And then both spring and split are applied, at least some of the split treatment is applied at pre-plant. And then now I'm adding the statistics here. So fall and spring, even though there is a peak in the fall in May, it's not statistically higher than the spring. So I wrote here, fall applied is equal to spring applied, but again, with the caveat of applied at a lower nitrogen rate to cold soils with an inhibitor. And then when you keep going, so now we're in September of 2016. So corn was growing through all of this. And then it's going to be harvested here. Another time we had very big fall precipitation. Now the blue is higher than the orange. So spring fertilizer, even though it's statistically the same, it's technically higher than the fall. So I just think that's interesting that the fertilizer treatments peak about 6 months after application. So October was when fall fertilizer was applied, and then here's the peak. And then spring fertilizer was applied here, and then here's the peak. So I had been talking about concentration, but now I'm just going to talk about load for a second. So load is the volume of water times the concentration. So when we think about like those large scale things in percent reductions, we're usually thinking about load. So it takes into consideration whether or not there was a large amount of water with a high concentration. And if you look at this graph, this is from 2015. Oh, I'm sorry, I wrote 2015 to 2016, but it's 2015 to 2020. This is over 6 years. All 3 fertilizer treatments are the same, but then, or the same statistically. Fall is technically the highest, but then if you compare that to no fertilizer, you only see a 23% reduction. So again, our nutrient reduction strategy goals are a 41% reduction, and even removing fertilizer completely only gets us to 23%. And I don't think removing fertilizer completely is even something that's possible or would be recommended ever. But it's just interesting to see that even without external inorganic nitrogen inputs, you only get 23% reduction compared to fall fertilizer. And then I'm going to touch on corn yield really quick. So I know this is a lot of numbers, sorry, but you look at the last line, all 3 fertilizer treatments were the same in terms of they have the same letter next to them, and then no fertilizer decreased, significantly decreased corn yield. And then that is true for all of the years except for 2017. So I highlighted the split nitrogen has a lower corn yield compared to fall and spring in 2017. And that was a very dry summer. So the urea was applied and then there was like no rain to bring it down to the crop. So in conclusion, fall applied and is equal to spring applied when applied with an inhibitor at maximum return to nitrogen to cold soils. And that's in terms of water quality and corn yield. Oh, and soybean yield was equal for all of them, which we would expect. Sorry about that. Split applying fertilizer had modest improvements to water quality and then a slight yield risk in dry years. And then I think the most important conclusion is that fertilizer management alone will not achieve nutrient reduction goals. So we'll have to use other tools in the toolbox. And I wanted to say thank you to my co-authors, Matt Helmers, John Sawyer, Carl Peterson, Landon Leonard, Andrew Weaver, and Terry Tuttle. And then, yeah, we'll have a moment for questions. But if you are getting your continuing education credit, here's the information to email Liz for that. And says by today at 5 p.m. And the next webinar is by Brian Doherty, and it is improving manure management to maximize agronomic and environmental outcomes next week. And I'll leave that up. Yeah.
Great, Emily. And no, it's not just my students that get to give webinars. So, because Brian is one of the alumni of our lab as well. So that's we try to have others. I'll just highlight quickly. This study is also part of a regional project, Nitrate project, and so this will be combined with information from other study sites. I think we have 8 study sites across the north central region of the U.S. and into Canada. And this project was funded by the Foundation for Food and Ag Research and the Foundation for Agronomic Research. All right, so we do have some questions here. The first one was the urea treated with stabilizer?
I don't think so, but Matt.
It was. So, yep, I do know that one, Scott. So,
okay.
Yeah, so with the urea, the spring did go down 2x2 as starter, but the in-season application was an agrotane treated urea to minimize volatilization because it was just put over the surface. So there it was agrotane treated urea there. Okay. So the next one is so they've for the last couple of years in Northwest Iowa and much of Nebraska, we've had pretty bad drought. Certainly, we've seen it at this site in 2021 and 2022. How might you suggest corn N rate recommendations be adjusted based on lack of precipitation or lack of leaching? And what sort of nitrate levels would you expect in water bodies draining from these fields?
Oh, that is a very good question. Again, Matt, please correct me if you have any, or chime in if you have any opinions. But
so maybe one thing to comment is, what did we see at Gilmore City following the drought of 2012?
Right. So if you have a dry year and then a wet year, the dry wet cycle is going to result in really high nitrate loss. Just because the nitrogen is building up in the soil, and then you get that flush of rain and it comes out. But in terms of nitrogen application,
so if we think of that, would expect that in years following drought, we would have more residual nitrogen in the profile. So we might be able to monitor that to help us with maybe reducing some of our corn nitrogen inputs for that year. So I'll just add one thing is that Emily's study the application rates were all the same for this study. We've switched that now starting for 2021, that we no longer have a fall application. We have a spring at MRTN. We also have a spring at a higher rate of 200. And then our split application is at 80 pounds at planting. And then the in-season application is based on what Soterius argentulus would indicate the needs are based on the precipitation that we've had to that point in time. So for example, in 2021, because it was dry, he recommended no additional nitrogen application in season. This year we put on like 30 or 40 additional pounds. So, that's one way we're trying to account for these weather differences that we might have. And so hopefully in one of these years, we'll have a very wet year, and then we'll see what the model indicates to predict. Okay, we do have some other questions here. I think a couple of them are thinking about that yield variability with the split application, maybe describing again why there was that low yield in 2017, excuse me.
Yes, I'm going to bring that up. So after you apply the in-season urea, you need precipitation to carry the urea down to the corn. Otherwise, it will just volatilize right away. So there was essentially no precipitation until like September in 2017, I believe, or maybe even after, but there was no precipitation, so that nitrogen just volatilized.
Sat on the surface. So yeah, but other than that, in any other year, we didn't see any yield difference between the fall, spring, and split.
Right.
Okay. There was a question, any no-till or cover crops at this site?
No, these were all, sorry, I should have said that. These were all conventional tillage and no cover crops.
We are, to be fair, we are studying cover crops and no-till on another site. So actually, I think, Emily, did you give a webinar on that study too that might be recorded from Gilmore City?
Yes. Morgan and I gave one.
That's right. Yep. Morgan
and that's
Davis.
also northwest Iowa. So I think it's interesting. Northwestern Iowa. It's not this particular research farm. But.
Okay. Next question. Do you think that the form of nitrogen rather than application timing had an impact on water quality?
Yeah, I'm going to go back to. So that's an interesting question. So the form of nitrogen, we didn't really study that. They were both applied, I think spring and fall. Yeah, they were both applied. Maybe the question is like urea, whether since we saw water quality improvements with urea, was that due to the form or the timing is perhaps the question. I think it's a combination of both because you're trying to balance the right form at the right time. So I think the fact that urea is probably more plant available than ammonia, but it's applied later, I think that's my prediction. Matt, do you have any thoughts?
No, I think that's right. I think maybe a little combination. I think more timing than the source, but so okay, since you're using the recommended nitrogen levels, we use the MRTN in this study, and most farmers apply or maybe apply more nitrogen. Would you expect a same or different response to timing and loading at these higher application levels?
I think at a certain point, if you're adding higher nitrogen rates, you're going to see increased risk to water quality. And I think part of why we saw what we saw that fall and spring were equal was that we were applying at MRTN.
So I always think of this as well, that I think if you, at least in that northern part of Iowa, where we do get, if we're putting on that nitrogen in the fall when soils are 50 degrees and cooling, if we apply the same rate in the spring and the fall, we may see similar nitrate concentrations from that, but there may tend to be a practice of applying more if we apply in the fall. And so in that case, we might see greater nitrate loss, but it may be more of a rate than a timing factor there. I certainly would expect that if we increase the overall rates from 135 to say 170, we'd see higher nitrate loss. And then, that percent reduction to no nitrogen would be more because the other nitrogen input treatments went up. But there's a question. So is it fair to say that timing does not appear to affect either yield or nitrate export? What about improper management? Is fall, for example, more sensitive to poor management? And so I can help with that because we've looked at that a little bit, Emily, if that's okay to jump in.
Oh yeah,
so
yeah.
So and it wasn't with commercial fertilizer, but we have looked at if we put liquid swine manure down earlier in the fall. In fact, Brian may talk about this next week, but we saw a pretty big yield hit when we applied manure early in the fall versus later in the fall, and an increased risk of nitrate loss. So I do think that fall, if we don't get it, if we were to get nitrogen down a little bit early, such that we convert more of that into the nitrate form, it might be more susceptible to loss. So I think it is, could be a little bit riskier period. Okay. In relation to the chart listing the nitrate loss difference of 23 pounds or 23%, is that chart showing the N loss over the 2-year corn soybean rotation or the loss when only N was applied?
That is a great question. This is over corn and soybean rotation. So this is like if you have a field over 6 years in corn or soybeans every other. So that N is 8, if that helps to answer it. A great question.
Were soil moisture levels measured annually in late fall, and at least not part of this study, right?
Right.
Okay, so there is a nitrous oxide isn't accounted in the nutrient reduction strategy, but it's an important greenhouse gas. Any speculation on quantities of NO2 loss from fall versus spring applied anhydrous?
I'm not comfortable speculating, but I will say that the project that this is with, it was 8 sites, right, Matt? And 6
Yeah.
out of 8 of them have simultaneous nitrous oxide or simultaneous greenhouse gas and water quality measurements. But I don't know
Yep.
enough, unfortunately, about
That'll
greenhouse
be
gas.
that. I asked that question only because that's how I figured you'd answer it. It's another plug for the regional project because what's interesting is prior to us starting that regional project, there had been only one study done that had at the same site at the same treatments measured nitrous oxide emissions and nitrate leaching, but that our study has 6 sites, and in the process of summarizing that, Emily, we did not measure it at this site, but there wasn't one in Southwest Minnesota that has measured it. So that'll be a topic for maybe another day. See here. Oh, this was the total rainfall and drainage measured.
Yes. Do you mean maybe like they're looking for?
I think it was did you measure? Were we measuring all the trying to measure drainage year round?
Oh, sure. Yes, but you have to shut down the pumps in Northwest Iowa around when there's a hard freeze. But there's not much going on. So this January to March winter is actually probably like very late March, and then we shut it down, or not, maybe not very late March, but in March, not in January or February, and then we shut it down in late December.
There's one here. Can you review the yield difference for the treatment without any fertilizer?
Yeah. So yeah, here's corn yield. It was significantly lower without fertilizer. I think this is pretty high for no fertilizer corn, but I think that has to do with the fact that like if you look, 186 was in 2015. That would have been the first year that this corn was like mining this soil for nitrogen, right, Matt? At least in the past like 3 years, because it had been oats and then soybeans. So, and then the no nitrogen just keeps going down as you go. And then I guess it does peak. I've never noticed this, but it peaks again in 2020. And 2019 was a dry year, so that kind of supports that in a dry year you have a lot of residual nitrogen.
Whereas I think in the year that we see the greatest yield difference is 2018, and I think that was
a wet year.
Wet year, yeah.
Yeah, that's true. Yeah, it's like 50%.
Yeah, we got a couple questions here, and then we'll wrap it up. And I think we're the same corn hybrids and soybean varieties used for the entirety of the
Oh, it changed each year, but it was always the same within a year.
But I think over that whole period we didn't use the same corn for the whole that whole period. Yep. Was whether you had a table like this for nitrate. I think you do in your paper.
So this was all published in Journal of Environmental Quality, and it's open access. So if you just Google Waring fertilizer timing, it'll be there.
And the last one, would soil health help with reduction with fall to spring and split in different tillage? And maybe you can kind of give, I'm thinking of it relative to what you saw at Gilmore City when you had where we have 10 years of no-till now.
Yeah, can you say it again? Would soil help with?
Well, I think the question is getting at, would you expect to see kind of different responses if you had no-till? Or would you expect to see greater reduction if we had no-till?
Oh.
And so I would kind of say, what did you see at you studied no-till for 10 years, version to no-till for 10 years. And
I think in general, no-till has kind of neutral impacts on water quality. So if you had
at least nitrate leaching.
Sorry, nitrate. Nitrate. If you had this exact same fertilizer timing study done on no-till, I imagine you would see the same things. But in general, we saw reductions within the first 5 years at Gilmore City with no-till, and that just kind of comes down to like these nitrogen transformations are a function of temperature. So if you influence temperature with tillage and you have the right amounts of precipitation and weather, then you can see nitrogen reductions.
But then that second 5-year phase, like from years 6 through 10 of the no-till, we saw no difference between no-till and conservation tillage, correct?
Yeah.
Okay, maybe you can pull up again, Emily, your slide for Liz for the CCAs, if anybody needs CCA credit. There we are. You can email Liz Ripley. Her email is ejucums@iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. With that, thanks so much, Emily, and thanks everybody for attending. Please tune in next week to hear from Brian Doherty, and I'll stop the recording.